In an earlier video, we asked the question, how would it be possible to measure the angle between two lines in three-dimensional space? And I brought along two pieces of this really neat pencil slate from Western Newfoundland to illustrate this question. So here are two lines arbitrarily oriented in 3D space. And if they're close together like this, we can try to put a protractor on them to measure the angle between them. But if they're in different places in the world, or they're not conveniently exposed on the same surface, then we can't do that. And we need to use a stereographic projection to find the angle between them. So in addition to measuring the angle between these two, we might also want to determine what is the common plane, because for any two lines in three-dimensional space, there is a plane illustrated by my notebook here that is common. Two lines, in effect, define a single plane. So we can also do that on the projection. And then there's a third question that we might ask, because for any two lines in three-dimensional space, there is always a third line that is perpendicular to both of them. And that, of course, is the pole to the plane that's common to the two lines. So if we can find that plane, we can also find the unique line in space that is perpendicular to our two starting lines. So let's see how to do that on the Inkscape stereographic projection. In the last video, we talked about measuring the angle between two lines, and we also plotted the orientation of two lines as points on the stereographic projection. So in this video, we're going to do that, and we're going to plot those two lines again, and we're going to measure the angle between them. The orientation of the first line was a trend of 123 and a plunge of 37 degrees. So we're going to rotate the net by 123 degrees and perhaps zoom in a little bit. We can zoom in and out with the plus and minus keys. And grab one of our markers. We will clone our marker again and take our marker here, and we'll move it 37 degrees in from the primitive, so as to plot the first of our lines. So now I'm going to reselect the net, and I'm going to do my Shift Option T to return it to the starting position. And this time we're going to rotate it to 155, which was the trend of the second line that we plotted. And we are going to take, let's do a magenta marker, and we'll clone it again. And we're going to do 155 and a plunge of 26. So we have two differently plunging, differently trending lines on our stereographic projection. So how are we going to measure the angle between them? So what we need to do is we need to click on our net, and we need to get those two lines on the same great circle. And I think I'm going to zoom out a little bit so that I can see what I'm doing to start with. And I'm going to turn the net around, and I'm going to try to get those two X's there to lie on the same great circle. So I think that looks pretty good, but I'll zoom in a little bit to check. Yeah, there we go. So those two lines are now lying on the same great circle. And we could actually draw that great circle, and let's do that. If we go to the spiral path here, and we're going to click 3 times in order to get a great circle. I'm going to follow this great circle here. So I'm going to click here, and then if I click down at the top point of the net again down here, I should have a great circle that goes through those two X's. And I'll right click to let go of it, and there we go. We have a great circle that goes through those two X's. I think I would like to make it a different color because it's the same color as the two X's and I can't see it very well. So if I just click on one of these colors down here, the result will be to fill in that great circle. That may actually help with visualization of the plane that it represents, but it's not what I want to do right now. So I'm going to click in the X to make it transparent. And this time I'm going to hold down the Shift key, and I'm going to click on a different color. Let's make it this gray color again. And now our great circle is showing up in a gray color. So In order to measure the angle between these two lines, what we need to do is to count the number of small squares along this great circle, and remembering that each small square counts for 2 degrees. So the way I will do this is I'll actually count 5 degrees to the next bold circle, small circle along that this path here, and then I'll add 10 here, so that makes 15. And if I go to here, that makes 25. And then I've got another 1, 2, 3, 4, 5 degrees here. So altogether, I've got 30 degrees. So the angle between these two lines in 3-dimensional space is 30 degrees. Now, there are other things that we can do when we have two lines in 3D space. We can find a common plane. There is always a plane that passes through those two lines. And in fact, we have already found that plane because we have drawn the great circle that goes through these two poles here. So all that we need to do is to find what orientation it represents. So to do that, I'm going to get hold of my net here. And one thing I need to do, I need to get this side of the net, the one with a little curve here, I need to get that side running along the great circle. And then I will be able to read out the strike and depth of that plane, the orientation of that plane that is the plane common to those two lines. So I'm going to get my turn handles here. I'm going to turn the net around this way because I want the grey line to be pointing towards the little curve on the side of the net here, so that we measure by right-hand rule. And then if we zoom in on this upper point of the net up here, we can see that our strike of this plane is 10, 12, a little bit less than 14, but I would say it's 14 to the nearest degree. So that would be 0, 1, 4, because we always use 3 digits for our strike. And then the dip is found by counting in from the edge down the side of that bowl, sunk into the ground, 10 degrees, 20, 30, 38. So the plane that is common to those two lines has a strike of 0, 1, 4 and a dip of 38 degrees. So we can also find the pole to that plane. And that pole represents a line with very special properties with respect to these two lines that we started with, because that pole is a line that is perpendicular. It's at 90 degrees to every line that lies in this plane represented by the great circle here. And therefore, the pole to this plane is the unique line that's perpendicular to our two starting lines. So let's get another little cross. Maybe we'll do a green one this time, and we'll clone it. And we're going to position it as the pole to this plane. So we went 38 degrees in from the edge. So we've got to go 38 degrees out from the center. 10, 20, 30, 38. So there is our pole. So it represents a line that's perpendicular to our first two lines. So can we figure out the trend and plunge of that line? Well, yes, we can. And to do that, we're going to take our net and we're going to turn it around again. We're going to put the arrow through that green X there. And then if we go round to here, we can read off the trend of that line. This is 280. So we've got 284 is our trend. And our plunge, how steeply is it going down into the ground? Well, we can measure that by counting squares along this line here. So that's 10, 20, 30, 40, 52. So our trend of our line perpendicular to the first two lines is 284, and its plunge is 52 degrees. So on this projection, we've done 3 calculations. We've found the angle between two lines, we found the plane that is common to two lines, and we found the line that is perpendicular to those two lines. And those are 3 calculations that you can do given two lines on the stereographic projection. And in the next segment, we're going to look at 3 calculations that you can do starting from 2 planes plotted on the stereograph.